Cool. I'm happy to go first.
Sure.
Cool. Spent some time with Vlad last week at a sharding retreat. Um, and we did a fair bit of work. Probably the biggest brunt of it, which is what I'll talk about, is the education stuff. So pretty much, we're Vlad's going to teach a CBC Casper like crash course, that's like extremely thorough, pretty much like starts at defining consensus and progresses all the way through understanding all of the CBC Casper protocols. It's going to be essentially a lecture format. We're still kind of figuring out exactly how it's going to work, and then there'll be quizzes and stuff to make sure people follow along. It's a partnership with the Blockchain Education Network, if any of you guys have ever heard of it, which is like a thing run by college students, which is pretty cool. But in any case, we spent a couple hours kind of flushing out like a curriculum on what we're actually going to teach. So we have a curriculum overview as of now. And then I spent like a day or two kind of like building out a full course plan, and also building out some experimental homeworks. So yeah, pretty much just like getting ready to kind of start teaching this class. We're not sure exactly how much work it's going to be to actually make these lectures. So like depending on how much it is, some stuff might be in scope, some stuff might not be. One thing I just realized, which actually might be cool, which we should discuss more at some point, is so one part of it is we're going to have like auxiliary lessons if we have time. Like for example, we'll have a small section on like crypto economics, incentivizing Casper, etc. And we're going to have a small section on like the overview of the current Casper proof of concept code base, right? But one thing that could be cool is if we had you Archain guys kind of talk about CBC Casper in relationship to what you guys are doing, and that's definitely something we should talk to Vlad about. But I feel like it might fit kind of nicely as kind of one of these like auxiliary things, if that would be cool.
Sure, sounds good.
Yeah. So the other thing, which I won't get too into because if Vlad shows up, I'm sure he'll want to talk about it. But we spent some time figuring out shard movements in the shard hierarchy. So like switching two shards, adding shards, deleting shards, changing the parent of a shard, and made some pretty good progress in terms of like figuring out how shards can actually switch places. At a high level, essentially the idea is that let's say that the shards 0 controls 1 and 1 controls 2. Sorry, actually, let me give you a more generic example. Essentially, if a shard is moving from being controlled by let's say an old master to a new master, then we pretty much just have to mine a merge block between the two of them that kind of says, ownership changes. And it turns out that's like pretty much enough to kind of do most of what we want to. But anyways, I'll let Vlad talk about that more when he gets here. Yeah.
Cool. That sounds exciting. Who all was at the retreat?
Ethereum folks mostly.
Got it.
Yeah. By the way, second thing, we have Paul here. Paul, do you want to like introduce yourself and go next, I guess, and kind of talk about what you've been working on?
Yeah, for sure. Thanks, Nate. So my name is Paul Hauner. I'm a software developer. I used to work in embedded systems, now I work in web. I started a company a few years ago with some close friends called Sigma Prime. We named it after, the world state in the yellow paper. So we've been working in Ethereum for a while. We've got about 6 staff now. We're doing smart contract auditing, consulting, and penetration testing and stuff. But myself and I guess the rest of the guys are really keen to contribute in this space where we can. So I was watching the C/C Casper talks from FCC, and it kind of got me interested. So I thought I'd check out the Python implementation, which was really cool, really impressive. I love the graphs from DEDCON 3. And I thought maybe I could implement it in JavaScript because, it's going to be the best way for me to figure out how it works. And it might also be useful to make some cool, kind of pretty, accessible diagrams of how it works. And maybe also, for easy experimentation's sake. After having a look through the Python implementation, which is really cool, I could tell that there's a lot of stuff in there. So I guess that's probably a bit more of a scientific implementation, whereas the one that I'm imagining might be, I don't know, help with teaching and kind of outreach maybe. So yeah, I've got most of it so far. I realized that I really underestimated the safety oracle, so I had to go through and re-implement that. I found the protocol really good. I found the paper really great to read. So now I'm just going to move forward.
So sorry, yeah. So you have a kind of a working first version of binary consensus, right?
Yeah, that's right. Yeah. So I've got it. It's like as a node module, and you can run it as a command line, and it'll output you just a bunch of like JSON data. So I'm working on this one so that basically you just you import it and then you call it and it just dumps you out an object, and then you just feed that object, which is like a log of messages, to a simulator, like a graphical interface, which then just renders it, statically. So I have the binary consensus stuff working, but albeit with not a fully complete safety oracle yet.
Cool stuff. Awesome. Yeah. Cheers. For anyone interested in checking it out, do you mind posting the link just in the chat here?
Yeah, for sure. I'll push it through now.
Cool stuff. Yeah. Welcome, man. Thanks for hanging out.
Yeah. Thanks. Yeah, I love the project. I'm really keen to be a part of it. Thanks for having me.
Cool stuff. Cool. Anyone else have any updates?
Yes, we do. We've made a lot of progress on our sharding and namespace development work, and sort of we finally have a proposal that has passed consensus, I think, within the Archain team that's concerned with this stuff. And I think Mike Stay is here, and he's got a summary of it. Mike, can I give the floor to you?
Yep. So this is what we're thinking for Mercury. Probably change when we get to Venus, but validators participant, the Casper protocol. Casper requires each validator to know what the entire set of validators is. So V is that set. We assume a non-empty finite set R of regions and a function mapping each region to this non-empty set of validators that validates it. Regions get to set slashing criteria for performance, network bandwidth, storage capacity, and so on. So if you're not able to play, you got to leave.
Sorry. So like, what is that? So like, the protocol asks you to store something and slashes you or kind of kicks you out if you can't.
Yeah. So if there's cryptographic evidence that part of the term was added and then you can't provide that piece of the term when it's requested, then you get slashed.
Okay. Do you have like a specific protocol design for that, or is that just
no? This is still very hand wavy.
Okay. Cool.
Set S of namespaces is the positive power set of the set of regions. So all the subsets except the empty one. For each namespace, little s, we assign a countably infinite set n sub little s of names in the namespace. The validators for the namespace S join T are the validators for S union the validators for T. So there are two different notions of union here. One is just this formal join operation that gives you a new namespace, and the other is picking out which validators validate that namespace. Deploying code in a namespace with many joins would be more expensive since more validators have to be involved. The execution may also be slower because you're taking the minimum performance criteria for the whole thing. Each term is colored with a namespace. So in Rolang, we've got input terms, output terms, evaluation, new, and so on. Each input expression is associated with the namespace of the names it is listening on. That's well defined because cross namespace joins are forbidden. Each output expression is associated with the namespace of the name being sent on. When you're sending or listening on a public name, that is one that can be constructed by quoting a process, it has to be annotated with the namespace. So at hello there doesn't define a specific name. You have to say at hello there : B or something. Every new production annotates each new name with a namespace to say where it lives. Other productions live in the nearest enclosing input. For this to work, we have to be able to move bits of code around. So for example, if we've got little b here that's living in the namespace big B, and y living in the namespace big Y, these two processes are running on different validators. So then we see that this this and this unify, they synchronize with each other, which reduces to Y bang Q, but it's still on B's blockchain. So then B has to transfer this thing over to Y and remove it from its own state. And we'll talk about how that happens in a minute. Similarly, we have the same sort of thing, but the continuation is an input. So A gets substituted with Y and reduces to this. So this should be in the Y namespace. It needs to transfer it over there. In order to do the transfer, Y needs B to be in a safe state. That is, there's no message that any validator in B could receive to make it not send or receive on Y.
So are you saying that we need like finality on the previous?
Finality is a little bit stronger. Finality suffices, but if Y can detect that there's no message any of the validators in B could receive before all the validators in B do, then that's sufficient.
So sorry, are you making a timing assumption there?
No. You can analyze deployed contracts to see what's possible.
Oh, sure. Okay, so this is an R-chain specific thing.
Yes.
Yeah, I got you. Okay, cool.
Similarly, B needs Y to be in a safe state so it can remove this thing here from its own state. Right? So there's some amount of synchronization that has to happen between those two to be sure that the handoff is completed properly. With joins between names that are not in the same namespace is a type error. If process is in the namespace capital B, a process in capital Y wants, if these two processes in B and Y want to race, they should both send send messages to a process in the namespace B join Y. So it's this special namespace that's set up for allowing races between otherwise disjoint code. If neither one knows about the other, but some third-party process wants to join on messages from both, the best you can do is to forward messages from B and Y independently and then join in B join Y. That doesn't match the semantics of a cross namespace join. It's impossible to do that in this system because semantics preserving one would suffer from a transitive closure problem. So if there's a race between a message from this process and that one, and then another race separately from that process and a third one, all three of them need to be lifted and know about each other, need to be in the same namespace. So this transitive closure of any process that is racing with some other one for attention, it has to be the closure of all of these that are racing with each other. Casper contracts, bonding, unbonding, slashing, and distributing rewards will be implemented on-chain as blessed Rolang contracts, similar to the Rev contract. The stuff that sends messages over the network will, in the first implementation, be done in Scala. Eventually that can move over to Rolang, but to meet the time constraints, this seems a reasonable approach. And we'll communicate with the blessed contracts via the tuple space. If you're not familiar with the tuple space concept, it's the database of names that keeps track of messages that are sent on names and continuations that are waiting to receive messages.
I mean, there's a more generic meaning of tuple spaces, but pardon me, which goes back to sorry, allergies. Which goes back to Galertner. Damn it. And we discovered that, or I discovered back in the 90s that it's trivial to implement pi on top of a tuple space. So that was the sort of the impetus of a lot of these architectures.
So when a validator does get slashed, every other one needs to know about it, because every validator needs to know who every other one is. So we suppose that validator little b in region big B is caught equivocating. To slash it, this is where we would like some help. We could use the top namespace in which everyone has to participate. The good part is that it only has to happen once. An alternative is to propose a slashing block independently to each region, saying, hey, this little b got slashed over there. But then there's the question of potential coalitions in these smaller namespaces that ignore the slashing block.
We also discussed a weighted least common ancestor idea.
Yeah,
where
so
you don't go all the way to the top, but you go, yeah.
So if you're concerned about a coalition in Big B, then you could join Big B with, say, region C, D, and E, so that the weight of, the weight of all of the validators joined together in C, D, and E would outweigh the coalition in B.
And this is if the coalition is in B is like kind of ignoring this slashing block.
Yeah. So is the ignoring the slashing block itself enough evidence for slashing for the other regions?
That's interesting.
So then another problem is that if a validator is joining a namespace joining a region based on its performance characteristics, they're essentially getting to pick where they get to join, with enough resources, you get to go wherever you'd like.
Yeah.
Can we fight the formation of coalitions in these namespaces or prevent them outright without opening up denial of service vectors?
Yeah, we need anti-centralization stuff, right? Because if you make the performance requirements high enough, then everybody just migrates to data centers where the performance resources are all concentrated already anyway.
Yeah, so that probably stands out as the biggest concern with validators getting to choose where they go. On top of that, it's in a variety of different economic models, it's less secure because pretty much if for example, we say that with the slashing thing, let's imagine we are doing this thing where the coalition in B can reject the slashing block, then suddenly it's a lot more dangerous if validators can kind of choose what coalition they're in, right? Because if they can all join a coalition and then reject a slashing block and just start doing evil things, it's not so nice. And so I'm sure Vlad has more well-formed thoughts on this, but I guess validators choosing what shards they're on or namespaces they're in, I guess maybe it seems scary to me. It seems like
so if a validator does get slashed, those that accept the slashing block can also slash any validator that uses a message from a slashed block in its justification.
Right, but I mean, yeah, I mean, okay. I mean, couldn't
So then-
those validators just ignore that though? Like, what's stopping them from just ignoring that slashing block forever?
They could, but then it becomes an off-chain question of which are
Well, that
the
becomes a-
authoritative
Yeah.
servers for the Archain network. If there are some misbehaving ones that slash but still claim to be authoritative, if you happen to ask one of them, who are the authoritative nodes of this network, they'll claim to be some. That said, they would also have to exclude everyone who thinks that they have been slashed. Otherwise, they'll.
Right. So my concern, I guess, is that now instead of them having to exclude everyone from the global validator set, they only really have to exclude everyone on their shard, right? Specifically, if you're a person who cares about activity on a specific shard. I don't know if that makes sense, but my concern is that it seems like it's okay to rely on non-censorship assumptions for slashing things in the global validator set, but when we start talking about like a subset of the global validator set doing non-censoring, and on top of that, a self-selected subset of the validator set, then it like becomes a lot more worrying, right? Because it's like a lot easier to do somehow.
Yeah. So we're trying to balance self-selection. So the protocol doesn't say self-selection. What it says is that the only validators that can be assigned to a particular region are the ones that match the criteria. It doesn't say what the selection criteria is.
Yeah. Okay. I hear. I mean, it's less random than just randomly putting people places. Right.
Right. And what Mike is pointing out is that if you make the resource, what we're trying to do is to get this basically a service level agreement idea for regions. So, but if you make the service level agreement language in some sense too discriminating, like if you say and a pair of ruby slippers, right? Then then only the exclusive club can get into that region.
Yeah. Right.
Yeah. Right.
I
so
hear you. I totally hear you.
Yeah.
Okay. I have a second question. But so like slashing for storage stuff. Cool. Thanks for sending the link. So slashing for like storage stuff, etc. Somehow it seems like we kind of get into like A, less attributable faults, and B, kind of like synchrony assumptions, because it's like, the protocol demands you produce some term and you can't produce some term. Well, it's without a synchrony assumption, it's kind of hard to say, oh, you actually didn't do this. It could just be, something else. But I guess maybe that's a different concern. But I don't know. My only question is like, I'd love to see like actual proposals for how to like slash people for these various things, because it seems like a hard problem rather than I don't know. But you can't just. It's not so easy, I guess.
We agree. We've been down this path and sort of been thinking about what constitutes cryptographic evidence for service level, provision.
Okay, cool.
Yeah.
Any conclusions or ideas?
Basically, we kind of think we can, you can do a composite storage and bandwidth thing. Whether or not, you're right that there's some kind of synchrony assumption, but at the end of the day, anyone who's doing, there has to be proof of storage stuff. Period. Right. I mean, you need sort of efficient cryptographic proofs for proof of storage, and there are a few protocols there anyway. So we think we can kind of muscle our way through that one.
Cool.
Some of the other ones are a little bit harder. Like compute cycle is very hard.
Oh, interesting. Vlad was talking about proofs of custody. He spent some time during the starting retreat talking about proofs of custody, which seemed related and relevant. So might be worth bothering him about that. But.
No, that's exactly what I was referring to. That's why. And there's a Russian hacker who has a similar sort of proof of custody that Vlad knows about. So I've been exposed to both of those protocols.
Awesome. Cool.
Yeah. So I think that's the R-Chain updates, unless Michael Birch or Kent have anything else.
I'll just mention here briefly that I had spent some time last week changing up my Casper simulator to take out all of the political capital stuff and put in some of the things that Kent and I had been talking about last week about referencing multiple parent blocks in order to come to consensus more quickly. And some preliminary result from that is if you insist that the two parent blocks cannot conflict with one another, then it's very rare for a parent to actually, or a block to get created that actually has multiple parents, at least in the situations that I was looking at, essentially because everyone is sort of putting in similar subsets of the contracts, right? So if you imagine that there's some total set of requests from users out in the network, and each validator can see some subset of them depending on sort of how the information is propagated through the network so far. Those subsets tend to overlap, and so they tend to make blocks that conflict with each other. And so it doesn't actually help the consensus very much, and it's very rare for two blocks to appear that are totally non-conflicting.
So this is something I thought about for the concurrent schedule thing in the Python code base. And I guess my question is, isn't that just like an artifact of like the transactions that you're generating in the actual simulator? Like, how are you so sure that that's, like in actual usage, it might be the case that validators don't see the same things, right?
Yeah, exactly. I mean, that's you had exactly the same thought I was having, which is that in the real world, right? You're people tend to shard automatically just because it makes their lives easier. They have to deal with less conflict. So you can imagine, there are natural things like natural groupings, like all the transactions from the Seattle metropolitan area between 9 and 5, and all the transactions from the Portland metropolitan area between 9 and 5. It makes people's lives easier to be able to describe these things in this way.
Yeah. So yeah, those are totally fair points. I will say that, yeah, the network model I've got is pretty simplistic for sure. The transaction model I've got is a simplified version of what R-Chain actually looks like, and I think it's sufficient enough to trust, at least when conflicts arise with transactions. But yeah, totally, you're right, Greg. I am not simulating any sort of agreement between validators. And yeah, if there was an outside protocol agreement between validators, then it could be made arbitrarily likely that non-conflicting blocks could be created. And maybe, I guess that's the conclusion from this, is that such an agreement would have to be reached between different validator sets.
Well, I think it will happen in practice, right? When people just those are models that people gravitate towards. But yeah, I mean, it's actually a very interesting result. What you have.
Yeah, so I guess as one extra bit of detail, the algorithm that all the validators were using was to publish a block that contained as many transactions as it could. That's what I was assuming that they were trying to do. which is why you tended to get overlaps frequently. It was basically everything that they've seen so far that's not already in the chain, put that in. And changing that strategy could give different results for sure.
Yeah. For example, you could make it so like every block just includes like a single transaction or something, which is like, obviously the other end of the extreme. But like Vlad had this like interesting thought about how like if you did that, then you could kind of as a user like detect safety sooner. Like imagine that you make a transaction, it gets included in a block, and then you say to yourself, as long as I don't make any transactions from this account for the next day or some amount of time, I can pretty much assume that this transaction is finalized immediately because it will never conflict with anything else because it's by itself in a block. And I control everything else it could conflict with. So like, yeah, I guess the point that I'm making is like, you can imagine that there are other strategies that might be like, useful for validators to do in terms of like providing services to users. But
no, but that's exactly why we want, a predicate based compression for transactions in a block, right? So you want to be able to describe sets of these things in a logical fashion, which then expands out to whatever the population is at the time. And then they can come to consensus, they can detect conflict just by checking to see if the predicates, are contradictory. And that you can detect because the formula language has a small model property. So if the model is empty, they're conflicting. And so then you only ever have to do any sort of consensus, on the off chance that you detect a collision. Cool. Right. And then they're going to be much less likely to have a collision because they're describing these predicates. Right.
Yeah. Cool. So I think that gets at what we talked about very briefly last week, in this version, you can't point at parents that conflict in the sense that they have the same transaction listed twice, but are not the same block. So, if I include transactions A and B and some other validator includes transactions A and C, then pointing at both of those would be invalid because, somehow we need a merge property, right? Which is something we talked about very briefly last week because that makes it much more general because then you could say, okay, pointing at both of these means that all three transactions A, B, and C come in together.
Oh yeah. Yeah. So,
Greg, and that is something that's currently not in there.
Okay. Got it. Understood.
So maybe that's where I should focus some effort is putting in like a reasonable merge discipline. But when I started thinking about it, like it's non-trivial to do that. So maybe we'll chat offline about it.
Yeah. Exactly. Yeah. Let's talk. Okay. Good. That's great. Great news. Any other updates?
Vlad said he is, quote, available soon, I think. So I don't know if we want to like wait for him, maybe for a bit.
Does he have some significant updates?
I mean, so the merge block.
Oh, he just joined.
Oh, yay. He made it. Yo.
Wait. Yeah, there is.
Yeah, there is.
Hey, everyone.
Yo, lad.
Hey, lad.
How's it going?
If he's talking, I can't understand anything at all.
Yeah. The connection
You guys hear me okay?
Yeah, I can hear you now.
You guys hear me?
Yeah, but I think there's a lag.
But you can hear me? Oh, cool. Yeah, I'm walking towards my courting date, or maybe through immigration and then my boarding gate. I'm not exactly sure. It's like I'm transferring, So how's everyone doing?
Good.
Did Nate tell everyone about the tree shard hierarchy reordering?
Yeah.
At a very high level, though. I didn't describe anything. I left it for you.
Oh well, geez.
I can go for it if you want.
Well, I'm happy to give the basic idea, which is that there are like we could basically synchronize movements between shards if they only move one, like shards that are like one layer down. So if we can move shards up, and so that like if I have shard 2 be a child of shard 1 and shard 3 be a child of shard 2, we can move shard 3 to be a child of shard 1 with a merge block between shard 1 and shard 2. And then we can move shard. So after that, we have like shard 2 and 3 be a child of shard 1, and we can move shard 2 to be a child of shard 3. We can also swap 2 shards, shard 1 and 2. And basically, the way it works is kind of if the merge block that is swapping them is in the fork choice rule, then any children of that, any descendants of that will be notified, and therefore can kind of participate in this swap in the sense that any blocks that include those shards will now now have to be justified by a fork choice rule that uses the new shard hierarchy.
By the way, you can't. Can you just swap 2 shards anywhere in the tree? Like, let's say we have like 2 intermediate level shards. Sorry.
There's like a relationship in the heights. Like they can't be 2. So far, we haven't figured out how to do more than a certain number of heights apart.
Well, I think so. I actually think that. So like we tried, we were able to swap like 2 shards when neither of their shards had any other children. And
we kind of argued that it didn't matter what shards, what children they have.
Okay, so sorry. Actually, we were able to swap 2 shards when one of the shards was the root of the tree. And so I'm actually making the argument that when both of the shards have other parents, it's not that easy to swap them.
Yeah. But the only operations we need is when either one shard is the parent of the other, or they have the same parent.
Yep. Yeah. Okay. So I guess the point that I'm making is that like when you swap intermediate shards in the tree, you have to do like a multi-step thing rather than just like being able to use this like switching the root thing that we had.
Yeah. I was kind of imagining the multi-step thing.
Okay,
but switching the root can be done in one step if we're switching the parent and like an immediate child of the.
But only if the parent is the root. That's what I'm claiming, at least.
That's an interesting claim. Maybe. Anyways, I'm about to go and try to transit through a desk here.
That was an interesting exit.
Cool. While he's doing that, and if anyone has any questions about the shard swapping thing.
I mean, right now, our notion of shards are a little bit disjoint. So
yeah,
it's gonna. I think they'll come back together at some point, but our notion of shard is really built around this idea of names, right? Once you have a notion of names, then sharding becomes a really it becomes it has a different kind of discipline on it.
So actually, Greg, I think there is sort of a clear parallel here, which is not between namespaces and shards, but between regions and shards.
No, I know that's the bridge. That's the term.
Yeah.
Yeah, that's the bridge.
So I think the main difference between Vlad's sort of framework is he's starting from the notion of a shard, which I think is most easily defined as being something with its own validator set or an independently replicated blockchain, and sort of building up. Whereas I think we've taken sort of the opposite approach, where we've been started with a theoretical notion of names, which is sort of the basis that we want to shard on, and then trying to map it down onto independently replicated blockchains and validator sets.
Yeah, that's right.
Cool. Vlad is gone as well, so I guess you don't have to wait for him to make it through.
Yeah, Mike Stay and I were having a spirited discussion about synchrony and finality, which I was very much enjoying. Mike, did you want to?
Looking forward to continuing that. Do you want to discuss it here?
See, how much time do we have left? We got about 15 minutes.
15 minutes, yeah.
Yeah. So why don't you go ahead and sort of describe for folks the.
Sure. So Greg and I have been thinking about distributed computation for a long time. And so we have focused almost exclusively on the asynchronous pi calculus. That is, when you send a message, you have no way of knowing when it has arrived. It's fire and forget sort of thing. Pi calculus does make the assumption that the network is reliable. So once a message is sent, you know it will eventually arrive, but you just don't know when. So, the row calculus, Rowlang itself, all these descendants of the asynchronous pi calculus were designed with distributed computation in mind. But it occurred to me that the blockchain is not distributed computation in the usual sense. That, in the Ethereum case, as currently deployed, it's a whole bunch of computers that are all simulating the same virtual machine. The whole point is to arrive at consensus on what this one machine is doing. It's not a bunch of independent machines communicating with each other. And so it is possible to know when a message sent on a channel within that one machine has arrived, because everyone has this view of the entire global state. Therefore, we could be using the synchronous pi calculus for modeling the internal state of that one large computer.
Sorry.
Go ahead.
By that, do you mean when contracts call each other? That's our equivalent to talking to channels.
In Ethereum, contracts call each other. In Rowlang, sure. If we're doing in our chain, the transactions are synchronizations on names. That's
sure. Okay. Cool. Gotcha.
So think of the Rowlang abstraction as slightly lower level than the Ethereum virtual machine. So the Ethereum virtual machine is like a kind of functional view, whereas the row version is going to be the function call is not something. Function call is implemented in terms of more primitive operations.
So in Ethereum, a transaction runs until it completes, and either you throw an error or run out of gas and it fails, or you get to the end and it succeeds. In Rowlang, you have to implement that kind of transactional semantics if you want them. The things that the validators are getting agreement on is which messages have been delivered to which mailboxes.
Cool stuff.
So the fact that they are getting consensus on when a message has been delivered to a mailbox means that we can use the synchronous pi calculus, is my argument. Greg is arguing that you need finality in some way, and I don't see why. I think there may be a sort of level slip going on there that between two validators, you don't know when a proposed block has been received. But that is independent of the machine that we are simulating.
Right. So what I was arguing was it requires that we take a step back and ask ourselves how does this machine interact with the world? So if the machine is doing a bunch of internal
interaction with the world is a separate question. I have
okay, no, right, yeah,
interacting with the world requires this sort of weak notion of finality that there has to be something that detects that this can't be rolled back anymore.
Right, but see, again, it's like from the point of view of clients of the machine, it's the stuff that the machine does internally in terms of a scratch pad is invisible. It's behind the event horizon of a black hole. We don't care.
Sure, but even in the asynchronous case internally, you still have to have finality to cause a side effect in the outside world.
That's exactly what I've been arguing, is that finality equals, message delivery, right? And the computer doesn't, except for sort of AIs that live entirely inside the computer, right? With respect to those of us who are building the computer to make it do compute for us, we need there's names that are entirely inside the computer are uninteresting to us. Namespaces that involve at least a name in the computer and a name that a client can both write to and read from are sort of the minimally interesting namespaces.
So I don't see what your objection is to using the synchronous pi calculus internally.
Oh, internally it doesn't matter, because we can't. There's no experiment we can use to see what's going on there.
Okay.
But as soon as you go external, which is where all the good stuff happens, right?
As soon as you go external, you need to have finality in order to send a message out of the blockchain.
You need to. I guess what I'm arguing is that's what I'm arguing is that as soon as you have interaction with the outside world, so this is basically closed world versus open world. In an open world, you have to have finality. Finality equals synchrony. That's what I'm arguing.
That phrase doesn't mean anything to me.
So you don't get synchrony without knowing that the message is delivered. And you don't know that the message is delivered without finality. On the other hand, if you have finality, you know the message is delivered, and so you can have synchrony. So that's the basic argument, that they imply each other.
But on chain, you are not tracking the receipt of a message that has been sent off chain.
On chain, you are they're how do I say this? I'm only interested, or clients are only interested in computations that both impinge upon the client and impinge upon the chain. So that's what I was describing as minimally interesting. Stuff that happens entirely in chain is unobservable, so we don't care.
Greg, are you making the point that for users to react to this, we need finality?
No. I'm not saying that we need finality. What I'm saying is, if we want synchrony, in the case that clients do a write to request a computation and do a read back on the result of a computation. Then, under those conditions, we have that finality implies synchrony and synchrony implies finality.
So when you say implies synchrony, do you mean it implies that the message was delivered at some point? Like the communication.
Yes. In other words,
okay, so it's not necessarily. Sorry. It's not necessarily that there is a message bound. It's that, like, for this thing to be useful to this user, it happened to get delivered in this time.
That's correct.
Oh.
Isn't the message being included in the blockchain delivery?
So that raises this whole other interesting question that I had to I wanted to keep simple for this discussion, which is that there's the observation of the clients of the chain, right? And then that raises all kinds of interesting philosophical questions, which are not really relevant. The interesting point is, if the client wants to be able to make a computation, so it's the classic problem for any model of computation, whether you're talking about genetic computation or anything else. That's the input, compute, and read back property that makes it a computer. It's not a computer if you don't get to read back and make decisions or determinations based upon the computation. It's some other device.
So are you talking about only looking at the blocks that are finalized in the blockchain?
No, all I'm saying is that if a client fires a missile as a result of some computation, and then the computation is rolled back, the client has no ability to roll back the missile firing. So the client is going to say, synchrony, like, I know the message got delivered is equal to finality. Do you understand what I'm saying?
So that sounds like you are arguing that we should be using the synchronous pi calculus.
No, I'm not arguing that at all. No, I'm not saying that. What I'm saying is that when you do that, you are making strong finality assumptions. That's all I'm saying. It's just that finality equals synchrony. Like,
okay, but in order to have any interesting interaction with the outside world can't roll anything back. Therefore, every interaction with the outside world is going to be a synchronous one.
Or the outside world can recognize, the outside world can take act. If the outside world wants to be more responsive, then it adopts a fire and forget model and only forces handshakes when it's necessary. I sent the information, but I wasn't required to get any acknowledgement on it before I go on with this part of the task. This other part of the task, I must get an acknowledgement before I go on with. So that's the responsive argument. And so responsiveness is what dictates when you use asynchrony versus synchrony. Is the connection still there?
Yeah, I'm still confused about the parties here.
Okay.
But are you saying that the chain is firing and forgetting because the thing outside doesn't have to tell the chain that it?
No. I was talking again. Sorry. I shouldn't have used I. It's just that the clients that wish to be responsive in other kinds of compute situations. So the thing about the client is just as much a computing agent as as anything else. The client asks this computer, this global computer, to get some work done on its behalf. And now it's not going to go and engage in any other activity that would, that couldn't be rolled back. In other words, is side effecting without some notion of handshake. On the other hand,
but
all
it
those,
doesn't seem like finality entails that properly. I mean, that can be done with, you can have finality without that handshake.
No. What I'm saying is finality implies synchrony. And this is basically just transaction. I mean, this is distributed compute. This is early results in distributed computing, right?
But
finality equals synchrony. And all I'm doing is to set the context in which we understand the meaning of that phrase. Like it doesn't mean, like, synchrony doesn't mean anything without side effects.
Sure, but it sounds like you're talking about atomicity, and we don't need need to guarantee that.
I'm not talking about what we need to guarantee. I'm only talking about the mutual implications in a world where.
Then you're saying we have no choice but to have that property if we have finality.
No, what I'm saying is if you have finality, then the message got delivered.
Greg, let's continue this at our. Right now we've got Dev stand up to go to.
Yeah, we got to jump. But this is a spirited and wonderful conversation. I really enjoy it. Thank you very much.
All right, bye everyone.
Ciao.